So we're here at the Rutherford Appleton Laboratory. This is inside Target Station 2 of the ICIS neutron and muon facility. So I come here to do a lot of my experiments because it produces a large beam of intense neutrons and sometimes also muons. These are very useful probes for matter at the atomic scale. So I come here to do experiments looking at the atomic structure of crystals and crystalline materials. And it's also a very nice probe for the excitations of materials like that, which is essentially what happens when you give them a little bit of energy. How do they evolve in time after you do that? So this instrument is LET, which stands for low energy transfer. It's used for measuring the excitations of materials. If you think about a magnet at the atomic scale, it's basically a series of atomic magnets. And an excitation of this would be to flip one of these atomic magnets, which can move through the crystal by trading places with its neighbor, so they both flip. On measuring the energy cost of these excitations and the way they move throughout the crystal is basically how you determine everything there is to know about the magnetic interactions between atoms in a crystal. So a really nice example of the relationship between atomic structure and properties is graphite, which is the material that is in a pencil lead. So graphite has a two-dimensional structure made of honeycombs of carbon, which are stacked on top of each other. And these stacks don't really talk to each other, so this is why when you write with a pencil, these layers will peel right off and remain behind on the paper, which makes them ideal for writing. They also have two-dimensional electronic properties. So graphite will conduct electricity really well in the plane of these sheets, but it conducts electricity very poorly in the direction perpendicular to that. This is the WHIS instrument, which is a neutron diffractometer. Neutron diffraction is used for looking at the structure of crystals, so the arrangement of the atoms in the material, the geometry and the spatial relationships between the atoms. Understanding this is really important because there's a really intimate link between the distance and geometry of the atoms in a crystal and the properties that that crystal will have. There's still a lot that we don't understand about the magnetic properties of crystals, and unfortunately the crystals, the gemstone style crystals that nature gives us very limited scope for exploring new magnetism. So we want to produce, and we are producing, a lot of specially designed crystals in this fashion, and this allows us to generate emergent magnetism. So the collective magnetic behavior of the crystal can't really be understood in terms of the magnetic properties of the individual atoms very well. And we hope to use this to explore some new physics and to eventually generate new technologies.